So I'm now going to talk about linear regression and how we can actually fit a line to data points using gradient descent. We're only going to talk about the one-dimensional case, and in the one-dimensional case that means we've just got single values, so they're one-by-one matrices in MATLAB. So imagine we've got a set of data points, right? A set of data points x1, x2, x3 up to xn, and we have a corresponding output for each input. So for each x1, for x1 there's a y1, for x2 there's a y2, and so on. So this is a supervised learning problem. We've got the input x, we've got the output y, and what we want to do is build a linear model so we can actually predict y given x. And linear regression in one dimension basically corresponds to fitting a straight line through the data. So if we've got this straight line, so imagine looking at a data set like this, which is just a weight against height of something. This particular data set looks as if it's lining up along a certain principal axis. So this will be a good candidate maybe for linear regression. I've drawn a line on here. If we can find this line that best fits, and we'll define exactly what we mean by fit, then what we can do is then after we've got the line, we could then use this line in order to predict what the height of something is given a weight which didn't correspond to a data point. So if it was 10, we just project up and then use this in order to calculate what the output is. So we have to start off with the equation of a straight line, which you should know as y equals mx plus c. Now in terms of individual data points, we have an xi with a corresponding yi. So we can always say things like this is going to be written in terms of specific data points. So in this case, yi equals mxi plus c, where xi is the input data point, yi is the output data point, m is the gradient of the line, and c is the offset of the line, right? So always the equation of a straight line involves finding the gradient and finding the offset. So what do the m and c values actually do? So if we look at the equation yi equals mxi plus c, what we can do is we could actually plot some lines for different values of m's and different values of c, just to give a feeling for what kind of effect they have. M is the gradient, so as you can see here in the first plot on the left, if we fix c to be some value like 6, as we change m from -5 to +5, we see what we do is we change the gradient of the line. And this is just to give you an indication of what kind of effect it's got. In contrast, if we fix m to some value, 1.6 in this case, then changing c, in this case from -5 to 15, just shifts the line up and down. Right? So this is the gradient, and this is shifting it up and down. So what we're going to do in this course quite a lot is generate data so we can fit it and then we'll know that we've got the right value, right? So what we're going to do is generate some stuff artificially using the equation y equals mx plus c. We're going to use, in this case, m equals 1.6 and c equals 2, and then we'll basically give it a range of input values between -4 and 6. So x goes between -4 and 6 with certain steps. We then predict, using y equals mx plus c, what the y value is, and then we'll, in this particular set of lecture slides, we're going to add in Gaussian noise in order to corrupt it to make the data look not untypically like something you might actually get in an experiment. So here we've got some x values, corresponding y values, but they're noisy. So how do we choose m and c if we've got a data set? How can we actually find them? Well, you could maybe try it searching them, maybe not random, but you can imagine try searching different values by trying a grid search of m's and a grid search of c's. Obviously there's a lot of combinations in order to do that, because you can only try something out at any particular discrete value. So in this case what I'm doing is I'm just changing the values of c between -10 and +10 for a few range of values, and again the same thing for m between -10 and plus 10, and plotting out a few values here just to give you a feeling for what kind of thing you end up with. And doing that, you can see, well, it changes the gradient, it changes the offset quite a lot, and it plots out different lines for different values of combinations of these things. None of them particularly fit, in this case, the data very well. So, you wouldn't generally want to do a fitting on the basis of just trying it and seeing what the line looks like. Does it look like it's going through the data points? We'd want a much more principled way of doing that. And in high dimensions, you've really got a problem. It's very difficult to know what's a good fit and how to visualize it anyway otherwise. So we want a nice principled way of saying we know how to calculate the best values of M and C to fit our data. So how can we do that? Well, the way to do that is to define what's called a cost function. So we want to say, how good is our fit, right? If we've got our line y equals mx plus c, what m and c values give us a really good fit? So what is a good fit? Well, we have to define an error, right? How far maybe the predicted y is away from the real y. So let's think about that. We can use the equation mx plus c equals y equals mx plus c. So for a specific data point xi, we can make a specific prediction yi hat of what that line is actually telling us. So given the m and the c we've got, we can predict from a given input xi what it thinks the yi is, and that's what we're doing here. We give it the x, we calculate what the predicted y is, and that's why it's got a hat on it. Now, if we can predict that, and we're doing it on our training data set where we've got inputs and outputs, what we can do is we can say, well, that's our prediction, but how far is it actually from what we think the output should be? So in our data set, we've got xi, we've got yi, which is what it should be, and now we can say we can look at how far what it should be is actually away from our predicted value, right? So now we're defining an error in terms of the actual output value that we want, and the distance it is from the predicted value of output that we're getting using the model we're using. And if we substitute back in the mxi plus c for the predicted y, we end up with the overall expression ei, so the particular data point value error is given by the actual y value take away the predicted y value, and the predicted y value is given in terms of the actual x point as well, right? So given the sample error, the trouble with this sample error is, and it's a sample error because it's just for one data point I, is that it goes positive one direction and negative the other direction as we go above or below what the actual if our predicted value goes above or below the actual target value. So consequently, it's got a sign to it. Now the danger of that is if we start adding up errors across lots of data points, and we have to do that in a second, if some of them have got a positive error and some of them have got a negative error, if we're unlucky, we might end up with virtually no error at all because the values have cancelled out. So we don't want that to happen. So in order to lose the sign, what we do is we actually square the expression. So we're gonna lose the sign. So we just care about how far you are away from the predicted value. Another reason for using the square is because it's mathematically very convenient. It's nice and easy to deal with because what we're going to see in a second is we're going to start differentiating this function, and it's easier to differentiate squared functions. So that's the error then, the squared error for a single data point. What we need to do now is calculate the error across all of the data points in our data set. So what we have to do is we look at this, that should be an I by the way, this error term here for a particular data point I, we have to then say we're going to add up this error across all of the i's. So when I is 1, we have this value, and we add it to the value we get when y is 2, and we add it to the value when I is 3, and we add it to the value when I is 4, blah blah blah, all the way up to n. And we can write that mathematically using the sum sign. So we're just saying here it's a sum. This is the sum now for I equals 1 to n across all of this sample errors. And the sample error, like I said, is given by the y value at that sample point, take away the predicted y value squared. Okay, so E is the summed error, n data points, xi is the input data point, yi is the output data point, m is the gradient, and c is the offset. So we can calculate the overall sum squared error over the data set using that expression. Right, now what we want is to know what values of m and c give the best fit. So when is E a minimum? We want to choose gradient and offset such that we get the best possible fit, therefore the lowest possible error. And right, we could do a sort of grid search and try lots of values of C and M and combinations of them. That's what we're just very, very briefly trying to illustrate here by just not randomly, we're just systematically searching the space a bit. Chances are you won't get, you're jumping in quantization steps anyway, so you won't actually ever get something which is a really good fit. But this is just to illustrate as we change the values in in M and C, we change the error, which is then plotted here. So because it's got two parameters, M and C, obviously there's two dimensions to this plot here, because we're changing along one axis, we're changing the M, and the other one we're changing the C, and this is then the overall error. And what we see is somewhere down here there's probably an M and a C value which look like they're giving a minimum, right? But we don't want to do things in this way. We don't want to calculate things by just doing a rough search of the space. We like a much more principled way, and that's where we're going to use iterative gradient descent. If we know, like we've looked at before, the gradient of the error function with respect to the parameter, what we can do is we can, if we got this gradient with respect of the error with respect to M and with C, what we can do is we can actually try to move the parameter value in a direction which points to the minimum error. So we just do it. We change the value of the parameter a little bit in the direction of the gradient, right? So that's what we do. We change it in the direction of the gradient until we try to get right the way down until we've got to our minimum position. And that's the idea of gradient descent and how we can apply it to this particular example. So let's think about, well, basically what that means is we need to know the error with respect to M and the error with respect to C. And if we do that, we can then basically say we're going to now make little iterative jumps in the value of these parameters down the error gradient. So to do that, we need to first of all rewrite our error expression. So we're starting off by, this is where we left off. So we're just saying the error, the summed squared error across all the data points. So across all the data points, and this is the error squared. So this is the predicted y, and this is the actual y for a particular data point I. We can write that down as just the sum of all the sample errors, where for a particular point I, the particular square error is given by the yi take away nxi plus c all squared, right? So we're just rewriting all of this just to make it easier. Now what we're going to do is we're going to say what we actually now want to calculate is dEdm, where E is the total sum squared error, and we can write that then by looking at this expression for the summed sample errors, and we can put the differential inside the sum. So we can put the sum outside, and then what we care about now is taking the derivative of EI with respect to M, right? So we're going to calculate, this is what we want to calculate, the sum of all the DEIDMs. So we need to calculate DEIDM. So let's do that. So basically what we see when we look at EI up here, we see it's an expression of something here being taken from something else. So this is just an easy expression. And then we square it, right? So this is a function a function of a function, basically. And to deal with functions of functions, we need to use the chain rule to differentiate. And what the chain rule will say is dEI dm can be written as dEI dUI dUI dm. And if you look at that expression, you can see that the dui's cancel because we've added one at the top and one at the bottom. So this is exactly the same expression as we started with. But now we can evaluate this by evaluating the first term and the second term and multiplying them. So let's now write in what EI is here. So EI is this expression here, but what we're going to say is the yi minus mxi plus c is going to be, we're going to call that ui, and then of course EI is just ui squared, right? So you've got two relatively simple expressions, and now we can calculate our terms for our chain rule, right? So we can easily see now, if this is EI, then we need to calculate dEI dUI. So we've got EI equals ui squared, so dEI dUI is simply going to be 2ui, right? That's really simple. We know that x squared goes to 2x, right? And similarly, we've got this expression here for ui, and we've got to differentiate that with respect to m. So everything which hasn't got an m in it is going to disappear because it's a constant. So the first term disappears, the last term disappears, and the minus mxi goes to minus x, right? And that's what we've got here. So we've now got our two terms for the chain rule, right? The dEI dUI and the dUI dm. So we plug them together to get the overall dEI dm, right? So here's the 2, that's the 2 times, and it's ui, so we put the ui, right, this term, we put it fully back in again, multiplied by the minus xi here. And then it's just a question of substituting this sample error, right, back into this expression here, which gives you the error across the entire data set. So that basically involves putting the sum back in. So we put the sum back in between I equals 1 and n. We take the 2 outside here, so this 2 comes outside here. This is the first expression here and the second expression, they stay the same. I mean, we can just slightly rearrange that. So we can take the negative sign out from the xi, and we move the xi forward. So this gives us a nice expression for dE dm, right? So that's giving you the error gradient with respect to the parameter m. And now we're halfway there. All we're going to do now is the same thing again for c. Again, the first bit's exactly the same. So starting with our expression for the error, the summed squared error across the entire data set, again, we just rewrite it in terms of the sum of all the individual sample errors, where the individual sample error is given by the y value, take away the predicted y value squared. Again, in order to calculate the gradient now with respect to c rather than with respect to m, we have to calculate dEdc. And again, we're going to use the trick of putting the differential inside the summation. So we need to calculate, don't forget, this is what we're differentiating. We want to differentiate this now with respect to c. So we take the sum outside, and it's dC of EI, which is the sum across I equals 1 to n of dEI dC. Just like we did before, to calculate the dEI dC, we use the chain rule, because again we got this expression is a function of a function. So we want to know what dEI dC is in terms of dEI dUI, dUI dC. Again, these would cancel out, so it's exactly the same meaning. Just like it was before, we end up with the EI is just the UI squared, where UI is this business in here. So it's the UI is the YI minus open bracket MXI plus C. And now all we have to do is calculate this bit here, dEI dUI, right? So we look at again, EI equals UI squared. So just like x squared goes to 2x, we end up with differentiating this goes to 2UI, nice and simple. And this one's even simpler now. So we've got to differentiate this expression here now with respect to c, right? So we want dui dc. First bit here is a constant, so that disappears. Second bit here is a constant, disappear. A minus c just goes to a minus 1, right? So that's that bit there. Then all we need to do is say, right, let's just put all our terms together to get the dei dc. So we're going to multiply this expression by this expression here. So we substitute in again the 2 times the ui. So that's this yi minus mxi plus c times times minus 1 there, right? Then what we do is we pop it back into, this is the sample derivative with respect to c. Now what we do is we put that into the sum again. So we put the sum back in. We take the 2 and the minus outside, and we end up with minus 2 sum across I equals 1 to n of this yi minus mxi plus c. So in order to do this least squares fitting then, this is just to summarize. We start off with the equation of a straight line for each data point. So xi is the input x and yi is the corresponding output. We need a cost function to say how good the data is. So what we do is we calculate first of all the distance from the prediction, the prediction, which is the mxi plus c, gives us our yi hat. We calculate how far that is away from y, and we square it because we don't want it to be a sign dependency, so we don't cancel things out when we start doing the averages across the data set. And then we calculate the total fit across all the data set by putting in the sum, right? So we just, this is then, this is the sample squared error, and then what we do is then we sum up across the entire data set, so between I equals 1 and n. To find the minimum, we need to find the gradient of the error with respect to the parameters. So we need to find the gradient with respect to m, so dm, and we need to find it with respect to c. And if we can do that, we can then actually do gradient descent, because if we know what the gradient is, what we'll do is make a small update to the parameter values in the direction going down the gradient towards the minimum. So just to summarize what the gradients then look like, we ended up with dEdm ends up being minus 2 sum across all the data points of xi open brackets yi minus mxi plus c, and dEdc is a little bit simpler, equals minus 2 sum between 1 and n across, again summing across all the data points of yi minus mxi plus c. So therefore it's quite easy given the data set to actually estimate what the gradients are. Now basically, in order to calculate the gradients, we need the current estimates that we've got. We need to know the current values of m, the current values of c. So when we're actually doing an update, what we need to do is at every step we need to recalculate the gradients for the next iteration, right? So here's some pseudocode that will actually do gradient descent then. Right? First of all, we initialize m to a realistic value over its realistic range. So if you've got mx plus c that we want to fit a particular data set with, I mean, you want to choose an m which is kind of what you think it should be. If certainly you wouldn't want to use something which was gigantic, because otherwise if you've got a huge value, it'll take a very long time for little iterative steps to get it to sensible value. Again, we do exactly the same thing. We initialize c again to a realistic value. Then we can have an iterative loop in order to do the estimation of what the parameters are. So there's going to be a loop. First thing we do is calculate the error gradient with respect to m, right? So that's the expression that we had before, dEdm, using this sum expression. We calculate the error gradient with respect to C, slightly simpler, DEDC. And then what we're going to do is going to update M, this gradient parameter, by moving downwards to a minimum error. Right? So what we're going to say is we get the value of M that we've got, and we take away alpha multiplied by the DEDM gradient terms, and then we update it. So M basically goes to M, what it was, take away alpha times the gradient. And alpha is going to be the learning rate. It's going to be how far we want to actually make a step down the gradient at that particular iteration, and it can't be huge. It's got to be something not too big. We'll talk a lot about this when we do neural networks. Same thing again for C. We want to move C in a direction, the parameter value in the C in a direction which is going to reduce the error. So the new value of C is going to be the old value of C, take away alpha multiplied by DEDC. So we're moving a little bit down the gradient for that as well. And basically you go around this loop, right, until first of all you've got to maybe a ridiculously large number of iterations. If you're doing this in MATLAB, in the lab, you wouldn't want it to run for days. You probably wouldn't even want it to run for more than a couple of minutes. So if there's something wrong, you might want to terminate with a maximum number of iterations. But you know, a more sensible way of terminating would be when the gradient starts going almost to zero, because that means you've got to the minimum, or you know, you've got to a low enough error. So this is quite easy to do then. This is roughly what you might want to do in MATLAB to do this kind of thing. This is just to give you an indication. First of all, we set up a random value for M, a random value for C. I'm using rand_n here because that's going to basically give you something with a zero mean. As we should know, rand_n is the function that samples from a Gaussian distribution, in this case one-dimensional. And what it's doing is giving you a value with a standard deviation of 1. So it's, you know, most of the time the value is going to be around 0 and not going to be hugely far away from that. I'm choosing a learning rate of 0.001. So basically I want to have little tiny steps to update the parameters with. The reason that you'd want to have tiny steps, by the way, is just think about walking up and down a hill. Imagine, like, even if you're walking up North Hill, there's a slight, if you come out of the university, there's a slight gradient going up to the top of the hill, which is maybe a couple of 100 meters away. So if you're going to make a step in the direction of the gradient, what you wouldn't want to do to get to the top of the hill is move, you know, 10 kilometers, right? Because you'd be way out of Plymouth. You'd be somewhere completely irrelevant. So the type of step you make is sort of dependent on the kind of landscape that you're actually trying to get up and down into, and it's exactly the same when we're doing these machine learning iterative techniques. So a tiny little gradient, and quite often you'll find it by trial and error in this particular course. What we're going to do now is we're going to set up our initial line. Initial line is mx plus c, and then I'm just going to have a simple iterative routine here which just goes through a number of cycles. So between 1 and 100, in fact. What I do on this particular example is then to say, look, I'm calculating the gradient now. It's going to be that expression that I gave you before. This is just implementing it all in MATLAB. So this is M gradient calculating using the sum function, the C gradient calculated using the sum function. And then here's the update bit. So the new value of M is the old value of M. Take away the learning rate times the gradient of the error with respect to M. And the new value of C is the old value of C. Take away the learning rate multiplied by the gradient of error with respect to C. And in this particular case, I'm also recording the error. I'm calculating the error. And then finally, I'm giving a predicted value out. So all I'm doing here then is just doing some simple plots. I'm plotting out, the blue thing is the test data that I'm using to fit. This is, the green line is as an initial guess, randomly set up with, you know, using rand_n of what the line might look like. This is going to be all over the place. You don't necessarily going to get this one. If you do it hundreds of times, you'll get loads in different locations. The red line is what it actually finds after it's been through 100 iterations, so it's actually a pretty good fit. And here you see I'm plotting out the error just to show you how things are progressing.